I think what I will do is, then the other thing is at the end of the hour, we are going to move a couple hundred yards from here and reassemble with the other groups, at which time I'm going to have the privilege of summarizing all the wise and succinct remarks that are made here, so don't let me down. I'd like to introduce our panelists first. I'll do that, and I'll do it very briefly. I don't do justice to them. And then we're going to start at the other end of the table and just work this way. And when that's over, then we'll turn to those of you in the audience. First, of course, is Ed Liu, who has a Bachelor of Science in Engineering from Cornell. He has a PhD in Applied Physics from Stanford. He was a NASA astronaut for 12 years, flew the space shuttle twice, and I believe he was the first flight engineer first American flight engineer on the Russian Soyuz. He spent 6 months on the ISS and is now program manager for advanced projects at Google. So it's an interesting job transition and a great perspective for us. Second, we'll hear from Bobby Braun, who has a PhD in aeronautics and astronautics from Stanford, some 20 years experience in doing design and analysis of planetary systems, and that includes the Mars Pathfinder missions. He was co-chair of the NRC review of the NASA Institute for Advanced Concepts, and he's currently NASA's chief technologist. And then lastly will be Doug Cook, who is a Texas Aggie with a Bachelor of Science degree in aerospace engineering. He has over 35 years of experience pretty much covering the main human spaceflight programs, the space shuttle, the space station, and now exploration programs. He's been assigned important responsibilities to carry out the program that we've heard about. In March of 1993, when NASA undertook the redesign of the ISS, he led the engineering and technical aspects of that redesign. He was a NASA technical advisor to the Columbia Accident Investigation Board, and he currently is the Associate Administrator for Exploration Systems Mission Directorate. So thank you, all three of you, for appearing. And Ed, why don't we start out with you?
Okay, I first wanted to make the point that this is all about innovation in some sense, because I think what the general public, what the United States taxpayer really wants out of NASA is for them to do innovative things that amaze them, right? They want them to do, they want to see value for their money. They want to see NASA doing things, right? And you hear people talking about it. I think the president probably used this word 4 or 5 times in his speech, probably used the word innovation 4 or 5 times. And you hear it everywhere. And the question is, how do you drive innovation? How do you get a group, as large as NASA to be innovative? And over the years, I've come to the conclusion that there isn't a special formula for it, but there are certain things that you can do that make an innovative environment possible. And to a large extent, I think that is the ability to move quickly. I think innovation really is speed in a lot of respects. And what that means is the ability to do tests of things, to try new ideas, see what works, to iterate, to try things over again. And that means a high pace of operations. At Google, we use the phrase launch early, launch often. And we apply it to projects that are launching. When people have new ideas, you can try them out. When you want to modify some piece of some product, you can do so to see what works and then either change it back or decide to go with it. And in order to do that, though, you need to have the infrastructure such that you can do things quickly. So we spend a lot of effort on building the system such that the launch process, launching a new product, is relatively easy. And not to say that the work that's done at NASA is like software. It is completely not. But the concept of building your infrastructure such that you can do tests easily and try ideas easily and bring them to fruition in, not in decades, but in years, and see what works and change it, I do think does hold over. In my years at NASA, I remember how often we were in a situation where we would have a good idea, and there would be no way to try it. There would be, if you could only get some flight test information, we would have been, we would have saved ourselves years of arguing, but instead, we may argue about it for years because there was no flight opportunity. So the lesson, I think, is really get yourself to the level of a rapid development program, and think like a rapid development program where your timescales are short. You're not necessarily trying to bite off gigantic chunks, but you're trying to bite lots and lots and lots of small chunks. And build a program around lots and lots of small chunks. And I think that is the kind of mindset that you need to be in to drive new ideas. That's what gets people thinking. That's what gets people excited when you have this opportunity to get lots of small victories. And when you translate that over to NASA, what does that mean? I think the equivalent of what we call launch infrastructure at Google, which is the ability to push new code quickly, try tests quickly, and so on. The launch infrastructure is really our, at NASA, which is real launch infrastructure, which is the launch systems. And so I would argue that moving to an architecture that has more rapid launches, lots of rapid launches, even if they're smaller, is worth the payload penalty you take. As you all know, the larger the rocket in general, the larger the payload fraction. But you're going to take a payload penalty from doing this. But I think you gain in an innovation bonus, in that you now have engineers have the ability to try things much more easily, much more rapidly, and without as much sort of risk of failure. If you set up your mission such that maybe you've got a mission every 6 months or 1 year, or maybe every 2 years you've got a test opportunity for your team. Boy, you're not going to try anything terribly exciting, because if you only get a test opportunity every couple of years, you better make sure that you don't try to, you don't do something too outlandish, because your next opportunity doesn't come up for a few more years. And I've seen that mentality at NASA. And I think that the way to change that is through a structural change. I think that to translate that back to launchers, perhaps a medium-scale launcher, perhaps a little bit larger than a Soyuz, or perhaps up to double the size of a Soyuz, that sort of class launcher, but where the requirement was placed on it that it could launch very, very rapidly without using up all of NASA's resources. And you get a lot of operational scale from doing that. The other advantage to this is not just in the development side of things, the development side of payloads and things in deep space, which is really what NASA should be doing, and we heard today, but from the pure operational side of things. The faster you get, the better you get at being faster. And we see that right here at Kennedy Space Center. When our launch rate was low, things became difficult. Processing became more difficult. The launch teams, the launch prep teams, everything became more difficult because they weren't in an operational tempo. Actually, the faster things got, up to some limit, things got better. Of course, there's something there. You can go too fast for any given system, and Shuttle did run up against that some years ago. Shuttle's limit is perhaps about 7 or so flights per year for that particular system. But what that means is that you should place the design requirement on your systems such that you can reach a high operational pace. I think that we should be shooting for something like once every week, once every 2 weeks, that sort of type of tempo with our requirements. And for real, I know they talked about that for Shuttle back then, back 30 years ago, and I think that there was some fudging of numbers when people said that the Shuttle was capable of launching that frequently, because it really wasn't. But if you go to a simplified system, a Soyuz-type system, but an American-made Soyuz system, I think we could do wonderful things with that. So I'll stop there.
Very good, thank you very much. Bye.
Great. Let's see. So, first of all, good afternoon. So I'm at NASA now, and so I had to make some slides. So Is there a way we can project them? Or would you rather I just talk? Oh, great. And why don't we go to the next one? It's one of the things I learned that we do in the government. We make good slides. Next slide, please. Yeah, so I've been thinking a lot about technology in these last few months. I've been thinking a lot, in particular, about NASA's technology programs. And I wanted to start by putting some of these technology discussions perhaps into a larger context. What is on this slide are the recommendations from a number of reports or guidance, recent guidance from Congress. And what I've been doing in my job, as many of you know, I've started just a few months ago. What I've been doing is reading about technology and about how NASA did technology in the past and how NASA has a possibility of doing innovation and technology in the future. And a couple of things have jumped out at me. The first is illustrated on this slide. There's been a very consistent set of external recommendations coming from a number of reports, including Norm's report most recently on the bottom of this slide, a couple of NRC reports. Actually, prior to the two that are listed here on this slide, there was an NRC report done about a year earlier that pointed out how limited and how lacking NASA's technology investments were. These two NRC reports, which both came out in 2009, one is called America's Future in Space, and the other is a review of the NASA Institute of Advanced Concepts, both pointed out the importance of technology and innovation for NASA, and in fact for the nation through NASA. In fact, both of these committees pointed out that NASA, over the past decade, had been effectively eating its seed corn, eating its investments in the future by being perhaps too mission-focused. At the top of this slide, I also have listed the NASA Authorization Act of 2008, where Congress actually came to this conclusion and spoke very clearly about the importance of technology investment in NASA. Can we go to the next slide, please? The reading that I've been doing has also been fascinating. This slide here illustrates a number of reports, very high level, a number of presidential commissions, several internal NASA studies, dating all the way back, if you look on the right, to the post-Apollo Space Task Group in 1969, and then jumping into the 80s with a number of reports like Pioneering the Space Frontier, the Sally Ride report on leadership, Norm Augustine's first report, and then most recently, as you move to the left, some of the more recent reports, including the latest Augustine report. What's fascinating to me are a couple points. What I've done here is listed the technologies or the capabilities that are called out in these reports. Each of these reports goes through and identifies in great detail the capabilities that are lacking and the capabilities that need to be invested in for NASA to advance beyond low Earth orbit. They identify the capabilities and the technology investments needed for NASA to go to all the places that you heard the President speak about today, and all the places that we in this room and as aerospace engineers or folks interested in our space program have been talking about really for decades. And what you see here is a marvelous consistency among these reports. That speaks to a couple of things to me. First of all, there are clearly some very well-defined capability areas that NASA does need to invest in if we're going to go beyond low Earth orbit. A number of independent panels have all come to that same conclusion. Second of all, and this is perhaps the disappointing part for me, the technologies and capabilities that are called for in a report like Pioneering the Space Frontier from 1986 are actually quite similar to the technologies and capabilities called for in the Augustine report of just this past year. And that, to me, speaks to the lack of progress that we've made. Of these reports, my favorite is actually, sorry, Norm. My favorite is actually Pioneering the Space Frontier from 1986. I would encourage any of you that are in college, in high school, that are maybe listening today or watching this, to get a hold of that report. It's really remarkable. The way that report starts out is with technology. The very first page talks about the importance of technology. In fact, what they do in that report is they start by talking about the way it was in this country in 1935. In 1935, we were just beginning transcontinental air travel. We were still actually delivering some mail, not very much, but some mail by Pony Express. And it jumps forward 50 years into the future to the time that that report was written in 1985. And it talks about all the technologies, many that have come about through our space program, navigation technologies, prediction of weather technologies, and many other technologies that nobody in 1935 would have been able to predict. These are largely what I would call disruptive technologies. Some of them had plans and had roadmaps and were well funded. Others were things that just came about largely through innovation. The report then talks about the year 2035, and it says, well, what are the technologies and what are the missions that will be available, that will be possible in 2035? And I think in 1985, that panel had a hard time identifying that. Just like it would be hard for someone from 1935 to predict the future of 1985, it's hard in 1985 or even today to predict the future of 2035. And one last thing I want to say about 2035, which I get from that report and also from the President's remarks today, it's important to realize that the students in our nation's universities will be 2/3 of the way through their professional career in 2035. None of us at this table will be sitting at a table like this, right? There'll be others. And they're in universities today, and they'll be 2/3 of the way through their career. My son is in 9th grade. My daughters are in middle school. They'll be halfway through their professional careers in 2035. We need to invest in technologies, not just for what it will bring to our space program today, but we need to invest in technologies for the capabilities that it will give that generation to do the things that we would like to do and that are talked about in many of these reports. Next slide, please. This is one of my favorite slides. It actually originated at the Johnson Space Center many years ago, and it shows, in my view, the value of technology. This is a slide which shows the mass requirements for a human Mars mission, which we heard a little bit about today, and which we all know is perhaps the grand challenge for human exploration. It's not something we're going to do soon, but it is something that we all want to do. And what's plotted there is the mass required, not on the surface of the Earth to start that mission, but the mass required in low Earth orbit, just to begin to send humans to Mars and have the capability to return them home safely. And what I think is so striking is the y-axis, right? It's plotted in units of International Space Station mass at core complete. We're almost there. We're almost at 1 today. And what you see here is that without an investment in technology, this mission would require something on the order of 12 International Space Stations in low Earth orbit. To be honest, I don't believe that's feasible. And in fact, that's quite a hard sell in Washington, I'm finding out. But through technology investment, and a number of the technologies required are listed on this slide, you can see that we could bring those mass requirements down from 12 to something like 2 International Space Station masses. Now let me tell you, that's still quite a challenge, right? That's not something that we can just snap our fingers and say, well, that's a done deal, right? It's taken us close to a decade to get to 1 International Space Station mass. So 2 is still a grand challenge. But it's in the realm of feasibility that we can actually talk about it. And it's, I think, a very clear example of the kind of capabilities that would be enabled through an advanced technology program, like the one that I and Doug are going to talk about today. Next slide. This is a summary of all of the NASA technology programs that we've been putting together. It's that relate to human spaceflight, I should say, not those pertaining perhaps to aeronautics or the Science Mission Directorate. This is a summary of the technology programs both within the Office of the Chief Technologist that I've been organizing and those that Doug has been organizing in the Exploration Systems Mission Directorate. And what I want to point out here is we're investing in a broad portfolio of technologies through a range of technology programs. We actually need a diverse set of technology programs. We need technologies that span, if you look at the bar on the bottom, we need technologies that span the entire technology readiness level, all the way from paper studies of advanced visionary concepts through flight testing of important technologies that will end up one day on missions. We need technologies that are planned from the top down, where we set high-level goals for our human exploration enterprise. We translate that goals into architectures and missions, from missions to spacecraft and technologies. And then we have a nice flow down that we can plan certain technologies investments. But we also need disruptive technologies. We need to invest in research and technology in a broad portfolio approach, because we don't know every advance that's going to be made over the next couple decades. Just like the folks looking back at 1935 certainly couldn't predict every technology advance, in particular, this one, the communicator from Star Trek, right? That was a hard one to predict, that it would come to fruition. The internet would be another great example for Ed.
I didn't do it.
I know you didn't do it, but still.
I use it.
Yes, we all use it. So what we actually need in NASA is a range of programs that span all the way from concept to flight. And through these programs, that's what we're going to do. We're going to take a number of the technologies that have been studied, frankly, for decades now, and that have remained in the realm of paper study, and we're going to take them into laboratories. We're going to prove them out, prove the fundamental physics that are holding those technologies back, take them into flight in a relevant environment, and make them real so that they can be adopted by our missions. Next slide. This is a wordy slide, and I'm not going to bother you with all the details, but there is one point that I do want to make here. And the point really is that, in my view, what the President's budget request really represents is a balancing of NASA's 3 core competencies. These are long-standing competencies that NASA has had since its creation in 1958. These are the technologies, one, of research and technology, which has long been an underpinning of NASA, of spaceflight hardware development, and of mission operations. And when I look at what the President's putting forward, and I hear the President speak about technology and innovation, what I see is really a balancing of that, where research and technology is brought back up into, perhaps, in my view at least, the proper balance with those other 2 very important competencies of NASA. In doing so, what that will enable is new approaches to NASA's current mission set, or entirely new missions altogether. It will allow NASA to be part of the innovation engine within this country, for NASA to sit, if you will, at the grown-ups table with the other research and development organizations that make a part of our federal government. And it's for those reasons that I think, frankly, that it's the right approach. Can we go to the next slide, please? I want us to take just a minute and talk about the Space Technology Program, because Doug's going to go into much more detail into the Exploration System Mission Directorate technology programs. The Space Technology Program was set up principally to be what I call a technology push program. All right? It's not a program where we're going to be investing in technologies for the next mission. In fact, if there is a technology for the very next mission, in my view, that should be sponsored by one of the NASA mission directorates. The Space Technology Program is set up to be outside the mission directorates and to look at what I might call broadly applicable or non-mission focused technologies. These are technologies that could impact a wide variety of customers and could affect a large number of NASA missions, missions of other government agencies, and industry missions. Now, the Space Technology Program is set up with 3 major divisions. We have an early stage innovation component, and this is a component that has been lacking for a number of years in NASA. And this component is going to go out and seek the best ideas, wherever those ideas may be, visionary concepts of our future. The Game-Changing Technology Program is going to take some of those concepts and take that little bit of physics that's holding that concept back and prove it in flight. And the final piece, the Cross-Cutting Capabilities Program, is going to take some of those technologies that we prove in the lab and take them into flight in the relevant environment. Next slide, please. This program is set up to work in a competitive manner. Almost all of the awards are going to be made competitively. It's going to be an open process that involves industry, academia, NASA centers, the other government labs. As I mentioned, it's a program that's looking for what you might call broadly applicable or non-mission focused technologies. And I've listed a couple of those technologies on this slide. Now these, by the way, that list is certainly not meant to be inclusive because many of the calls for this program are going to be wide open. We're going to be looking for ideas from the community. And we will sponsor and fund those ideas really based entirely on the merit of the research that's proposed. Next slide, please. So I'd like to close with just a couple of thoughts, and they're listed on this summary slide. One, there have been a consistent set of recommendations made both by Congress and a number of external panels that have driven NASA to the development of the technology approach that we're putting forward today. Two, our planning process is really moving rapidly, and actually it's, in my view, it's going fairly well. We're putting a lot of detail into these technology programs, and we're going to be ready to roll those out at the beginning of the fiscal year. Three, through these programs, both the Space Technology Program and the ones that Doug will describe in a moment, we're going to develop new technologies, new capabilities that are going to allow NASA to do an entirely set of missions. We're going to use these capabilities to get humans into deep space. We're going to use these capabilities to improve our robotic explorers. We're going to use these capabilities to improve our knowledge and understanding of the Earth. And then finally here, I want to definitely point out that a NASA focused on innovation and technology is important for the agency, but it's also important for the nation. NASA serves perhaps a unique role to inspire and motivate our young people into educational and career paths in science, technology, engineering, and mathematics. I know that firsthand. I'm a product of NASA's educational programs. NASA got me hooked at a young age through a summer program at the Langley Research Center, and they actually kept me involved in graduate school through the Office of Education and some of their programs. These programs are very important to me. You know they're also very important to our administrator, Charlie Bolden, and they're also very important to this nation. It is a unique capability that NASA can provide. In addition, I also want to point out that the NASA centers are full of intellectual capital. And that intellectual capital, while it's working on some of the greatest challenges in human spaceflight or in exploring our solar system, that same capital can also be applied to major national needs here on the Earth, major societal challenges like energy, prediction of disasters, weather, national security. These are all things that integrate and cross right into our space program. And so that is certainly another area that these programs can contribute. Thank you.
Bobby, thank you very much. Doug, your turn.
Yes, sir. While my chart's coming up, I'll just outline our organization has a current Constellation program, as well as in the new budget request, we have the commercial crew efforts and program that will be getting started. So I wanted to mention that. We also have a very robust technology portfolio and demonstration effort and research effort that we'll be going forward with. I'm going to concentrate today and focus on what we're doing in the area of research and technology. And I think the things that Bobby has talked about are overarching and directly apply to the things I'll talk with you about. Actually, we will be working closely together to make sure we coordinate the overarching aspects of his particular responsibilities, as well as the more focused efforts that we'll have in exploration technologies. A number of the emerging technologies that he will be working to develop will find on-ramps into our programs in technology. So that will be an important facet of our relationship at NASA in the future. Let's see where we are. Okay. So if we can go to chart 2, what I wanted to do is pull all of this together in a way to visualize what we're talking about. If we look at the destinations that are possible for human spaceflight, there are a number of possibilities with our grandest vision ultimately sending people to Mars. And you've heard about the various destinations in the discussions. I do want to say that it's important to understand what it takes to go do these missions. Just yesterday, we kicked off the Human Exploration Framework team that's an agency-wide team to go develop the design reference missions, if you will, for going to these various destinations so that we can work into them the impacts or leverage that you get from various technologies. As you go look at these destinations, you learn that there are certain capabilities that it takes to send people there, and many of them are common between the various destinations. So it's important to understand that so that we, in the future, plan our programs in a way that get us the most capability and versatility in our launch and space infrastructure. All of these lead you to a set of capabilities and technology and research that it takes to go do these missions. And you find that, and Bobby had the perfect chart, which is one that we originally did a long time ago, but shows the leverage of the various technologies that it takes to go to Mars. And you absolutely probably cannot do it unless we go invest in these technologies. They're absolutely essential. There's a list of them. They've been repeated in reports. Actually, I've been on a couple of those reports myself over the last 20 years. And they are called out time after time, and they're areas that we have to invest in if we're going to go beyond places we've been before. In terms of the little green boxes at the bottom of the chart talk about breakthrough technologies. These are the kind of things that will come out of the work that Bobby does that leads into new possibilities and on-ramps for certain technologies that will be critical to us as well. And we'll find leverage in making these destinations. So this, I think, kind of pulls together the thinking that it takes to understand what the critical technologies are. If we can go to slide 3, this chart lays out the various technology areas that are in the exploration President's budget request. It starts with the exploration technology and demonstrations, which includes flagship technology demonstration program. It includes enabling technology development and demonstration program. These are two different areas that I'll talk more about. It also includes heavy lift propulsion technology, including first stage engine development. It includes upper stage or in-space engine demonstration, and it includes foundational propulsion research. These are areas where there are very enhancing technologies that need to be developed in order to make our launch vehicles more efficient and easier to operate. The next area is exploration precursor robotic missions. I won't be talking about that because it's being talked in another session, but it does factor into this whole approach in that these robotic missions that we'll be planning in our programs will be the opportunity to go learn about the destinations that we'll send people to, but it will be we'll be able to demonstrate the technologies that are essential for human spaceflight to the destinations, and we'll be testing in the relevant environment. So these will be focused on that kind of knowledge. We also have the Human Research Program, which has increased funding. All of these will be robust areas where we will be investing in research that it takes to send people into space. If we can go to the next chart, we get into more of the exploration technology development demonstration. These are many of the same technologies that are listed on the charts that Bobby showed that have been identified over a period of time that are incredibly important to us and have high leverage and actually are essential in terms of going beyond the places we've been before. Advanced in-space propulsion is a big driver. Getting to high-efficiency in-space engines is critical in getting the mass down in low Earth orbit, so that in terms of fuel that it takes to get to these destinations, particularly the long duration flights to places like Mars. Autonomous systems and avionics will help us to operate more efficiently in space. Cryogenic propellant storage and transfer is one that we will need as we work in space with large amounts of fuel to go to long destinations far from here and not have the boil off that occurs in some of our propellants. Entry, descent, and landing is a critical technology, especially with the large masses that it takes to send people to surface locations. Developing precision landing and hazard avoidance so that we can land in very interesting locations on other planetary bodies is important to us, as well as the aerodynamic braking technologies that we'll need to enter atmospheres. EVA technology will be important because our suits have to get lighter if we're going to other planets. Surface suits can't be as heavy as our current space suits are. High-efficiency power systems are also important in order to get down mass, in order to be able to actually have enough power in a place like Mars with reduced sunlight, since it's farther out, in order to operate there with people. Human robotic systems, robots and humans working together expand our capabilities when we send people to achieve the science goals and exploration goals that we'll have, so that we make people more productive when they get to these locations. In situ resource utilization is the use of indigenous chemicals or minerals at a location like Mars to develop your own fuel to make the trip back, so that you don't have to carry all that fuel with you. Life support and habitation systems. It's important to get to closed-loop life support so that we don't have to carry all the logistics and resupply in terms of water and air. Lightweight spacecraft materials and structures are incredibly important to us in terms of getting mass down. All of these we plan to have demonstrations for over time, where we will have different demos on different capabilities, whether they're in this arena or in the flagship missions, in order to demonstrate that and reach the higher readiness levels that we need to go into development on systems. We go to the next chart. This addresses the human research program. I hope. Not being able to see it is a little challenge. Biomedical technologies are important. We need to keep our astronauts safe as we get into these various missions. There are different hazards that they have to deal with, and we have to keep them safe in order to achieve the missions. We will be doing a fair amount of this on Space Station. It is a critical resource for long-duration missions in microgravity. Space radiation research is incredibly important to us, as we will be testing, understanding the effects on human cells of intergalactic cosmic radiation. It's a radiation that's out beyond our, that affects our astronauts once they get outside the Earth's magnetic field. It's not as much a danger in Space Station, but once we go on these long missions, we'll be out in it, and we don't yet understand totally what the effects are of that radiation. So that could be a long pull for us for long duration missions. Behavioral health research is important from the standpoint of understanding crew interactions over long periods of times on these long trips. Space station utilization, as I mentioned, will be critical, and our investment will be increased there over what we have been planning. We'll be learning more about the human risk associated with microgravity that they will experience both in orbit around the Earth, but also on long duration missions. We'll be adding new content to that research through research announcements that will add to the things that we'll learn there. If we can go to the next chart. Next, I'll move into an area that is very, very exciting for us, which is the flagship technology mission area, where we will be testing at larger scales and gradually larger scales different capabilities that are essential to us. Some of what our teams have mapped out in the last few weeks are listed across on the left-hand column, which are propellant transfer and storage, lightweight inflatable modules, automated rendezvous and docking, closed-loop life support, aero capture and entry, descent, and landing, advanced space propulsion. And we have a number of missions across the top, which are candidate missions at this point, but we have put together some ideas to get the existence proof. What is it that we can accomplish within the FY11 budget request? And so you see X's on, for multiple X's on certain of these missions where we can accomplish objectives for some of these technology areas in a single mission. If we go to the next chart, this is an example. As we put together our advanced space propulsion, we can start with existing capabilities, the kind of capabilities that have been developed in ion engines for missions like Deep Space One and Dawn, and begin to do some of our, begin with a bus basically that can do multiple missions for us in these technology areas that will gradually increase in capability, building to higher megawatt or higher kilowatt and then megawatt class in-space power capabilities, whether it's solar power or fission power, as we get to ultimately the high efficiency propulsion capabilities, whether it's plasma engines or nuclear thermal propulsion. Go to the next chart, please. This one talks about in-space propellant storage and transfer. These are some ideas on how we might start that with one of these buses that I mentioned earlier, having 6-month stay with cryo storage, working through and employing the technology in cryo cooling and maintaining the cryo fuels in space. Also, the first step would probably be to transfer some of this fuel on board a single spacecraft. The step beyond that could be multiple spacecraft where we're testing out connectors and flow through between one spacecraft and another. In that type of scenario, we'd also be checking out automated rendezvous and docking. So as we move through these steps, we gradually increase our capabilities. We understand the technology is engaging, understanding how much fuel that you have in a tank, how much you've transferred, which is not simple either, as we work through understanding these types of technologies. The next chart talks to inflatable technology. Here we would start with small inflatables on station to test out that technology. We would grow over time to larger modules that are inflatable, where we could scar for life support systems and a capability that we've worked out in the last few years called suit ports, where you actually get past the idea of airlocks, and you can actually transfer directly into suits from your spacecraft. Obviously, space station is the location where you can also test out new spacesuit technology. Next chart. We also are looking at a roadmap, and we'll be working closely with Bobby on this one as we bring in the emerging technology inflatable heat shields, where it combines new technology in both aero and aero heating with inflatable shapes. And this just shows a progression through the types of demonstrations that we would do in the flagship mission to demonstrate these types of entry vehicles. We would also look at not just blunt shapes, but mid-L over D shapes, lift to drag shapes that would be able to maneuver a little more in a Mars environment. Mars is going to be a unique concern in terms of entry, descent, and landing, because you can't just use a heat shield and then put the chutes out and land with the large vehicle that it takes to send people. So that will be a unique case that we'll have to develop with a lot of propulsion during descent, potentially early use of the hypersonic inflatable shapes to slow it down, and then the precision landing and hazard avoidance once you get near the ground. Next chart, which is the final chart. So I think when you pull all these together, all these ideas together, you see that this program does seek to extend human presence throughout the solar system. Our budget request this year, the FY11 budget request the President talked about today, will focus on these capabilities that I've outlined in terms of getting us to potential destinations, moving out beyond Earth orbit to places we have not been before, and staying for lengths of time in those places that we have not done. This investment will focus on learning, getting information and knowledge about the locations that we go to, that we'll send people to, as well as developing the capabilities to get there. So the approach expands the alternatives and the unique capabilities that are needed that are through strategic investments that are very much needed in order to be able to conceive of going to some of these distant locations. And with that, I'll turn it back to Norm.
Okay. Doug, thank you very much, and thank each of our panelists. We now are at the point of the session where we turn to those of you in the audience to make comments, ask questions, offer suggestions, propose new ideas that we should have thought of. So who would like to start out? Please.
Yes. Ed talked initially about the need for organizations to be agile in their approach to these activities in order to be successful. At JSC and at NASA, we have complex system engineering processes in place which have been codified and institutionalized into the organization. And while they're very thorough in what they do, they're not really what you would call agile. How can we create that kind of agile environment that we need in order to take on these challenges that have been described?
Well, that's a great question. Ed, I think we'll start with you, and then let either Bobby or Doug follow up if they wish.
Okay. I think that's a great point, Andy. And I actually wanted to ask a question of Doug first, or maybe a comment. My thought was that there's so many things that you want to test out there. My actual feeling is that unless NASA changes the way it does business, as Andy alluded to, none of that is going to happen, meaning not at a pace that will really lead to what the President asked for. That will take essentially forever at the way NASA does things. And I think there is a sort of form follows function thing in that you need to set things up such that it is easy to do a flight test, because there are so many flight tests required to do all those things you mentioned. There must have been 50 up there or more, 50 or 100 different flight tests required to just initially test all the technologies you list up there. And if you're testing one of these every 6 months, then you can count the number of years and you can see that that's never going to happen. So I think, again, to make the system operate fast, we need to build a system that's capable of moving quickly. And that means very rapid turnaround.
Yes, and I think by the nature of this program, these sets of programs that have been laid out, we will be putting pretty much in rapid motion these flagship demonstration missions, the robotic missions. We'll be combining some of these technologies, of course, with on some of these missions. We're planning to start 4 flagship technology demonstrations in FY11 with more to follow thereafter. And we'll be working on the first few robotic missions as well. We also have, which I didn't mention, I meant to, scout mission capability, which will be very small spacecraft, possibly grouped on a single launch vehicle that can demonstrate or provide information on for multiple purposes. So I think you're right. I think in order to get through this, we'll have to be agile. I think by biting biting some of these off into chunks that are shorter term, and more often we'll get to that point.
We've got a lot of folks standing in line with questions, and so what I'm going to ask is that we'll probably just have one panelist address each question and ask you to be relatively brief. Please.
Excuse me, MJ Swallow, University of Central Florida. The comments about the predictions in 1939, I think after the Second World War, we gathered all the Nobel Prize winners together to say what's going to happen in the next 50 years, and they missed almost everything. With that comment in mind and thinking about what Ed said about doing experiments, lots of them, what about a different architecture for the research that involves, by way of analogy, some of the things that have been done with PCs to string them all together to make one supercomputer, but instead of that, human capital. We have lots of chaos at universities. Every year we get a whole new class of chaos at universities. What about putting some emphasis on suborbital flights? There's lots of experiments that can be done in suborbital flights, zero gravity experiments, structural experiments, propulsion experiments, et cetera, on a very small scale, very rapid turnaround that would involve lots of people. I think the problem now with NASA missions, from a university standpoint, it sometimes costs us millions of dollars even to compete for one. And there are years and years and only a few people play. So if we can engage a broader spectrum of the intellect that's out there, that's interested, hungry, enthusiastic, young, don't know what can't be done, et cetera, I propose that perhaps an architecture using distributed kind of research with using suborbital flights to address many of the things that were on your list might be useful.
Thank you. Bobby?
Yeah, so it might not, so as a former university professor, it probably doesn't surprise you that I would agree with your statement. And one of the things that we're working on is to capitalize, if you will, on all possible platforms, right? When I talk about relevant flight environments, right, each technology has a relevant flight environment. And it's important that we choose the lowest cost or the most accessible test beds so that we can do many tests of that technology in the relevant flight environment. If something can be proven on the ground, then great, let's do it on the ground. If it requires a high-altitude balloon or a sounding rocket flight, let's do that. Not everything has to be its own low Earth orbit flight test, or we don't need necessarily to go out to Mars, for example, to prove every technology, just to prove it in the space environment. So I take your point very seriously. And in addition, I do want to say that through these programs where we're going to have a steady cadence of flight testing, where we're going to have a steady cadence of demonstrations and test programs, not just paper studies, we do intend to involve a broader community, in particular the university research community and industry.
Okay, we got a light there. Bo, is that you?
Bo Baymack. I've got a couple of questions. One is to Ed Lou. You said that, and by the way, I think if somebody comes from Google, it used to be like a pinnacle of innovation. But you said something interesting. You said, we haven't found a formula that would single formula to foster or bring about innovation. But what I was wondering, have you found things, by contrast, from your experience from NASA and Google, things that inhibit innovation? Because I have seen some, and I wonder what you think when you look at two organizations, NASA and Google.
Absolutely. I think that when things are difficult to try new ideas, and when your opportunities are infrequent to try new ideas, that clearly quashes innovation. And unfortunately, I think we're sort of in that state right now with NASA. If you have some new idea and you're looking for the next available flight opportunity, it might be 5 to 10 years out. What are your chances of trying that? It better be pretty fairly developed before you really get a chance to do it. It depends upon the size of it, of course. There are some small-scale experiments, but they're not a lot. And if what you're would like to try has any significant mass to it, you are looking at 5 to 10 years out.
Yeah. One thing I noticed, and Doug, maybe you probably can relate to that. I noticed that during constellation development, NASA has put very firm, rigid processes in place during development. And I always felt like, during development, especially early development, you need flexibility to foster innovation, give people a chance to think a little more independently. and as you approach toward firming what you want to build and building it, then you need to tighten up that discipline and processes. And I felt like NASA perhaps started too early with governance and processes, and I think those slow down decision-making process and also stifled innovation. But I don't know, do you agree with that, Doug? Or?
Certainly. Absolutely. We have to work to streamline our processes. That's what Ed is alluding to, and we have started looking at that already, and we have to be more agile. This approach to developing the technology and capability will tend to drive you to that. If you're on short turnaround and developing a quick turnaround demonstration, I think you'll have to get in that mode. So maybe this is a forcing function.
Bo, thank you very much.
Could I add one thing to that? It's not just the processes, but actually having some physical infrastructure that allows you to do that. For instance, could you imagine what we could do if we had an American-built Soyuz class launcher that was, I have no doubt in my mind that we could do it better than the Russians. And I'm a satisfied customer of having flown a Soyuz, but can you imagine if we had something that could put up, say, 10 to 15 tons on that price point at which the Soyuz does it, which I think we can do, and you could launch it every week like a Soyuz is capable of? What would we do with that?
Oh, yeah. Bo, thank you. We've got two more people, and so we'll do these quickly. And please, go ahead.
Steve Squires, Cornell University. One of the main things that I'm doing these days is helping to run the NRC's planetary decadal survey. And one of the problems that we have identified as a big, big issue is what we've referred to informally as the TRL Valley of Death. Historically, NASA's done a great job of taking real low technology readiness level ideas and moving them to sort of mid-range technology readiness, but getting them to the point where they're ready for flight and where a project manager is ready to accept the risk of using that technology has been an area where we believe the agency has fallen short. And so my question for this group, and I guess particularly for Doug and Bobby, is in the President's plan for NASA going forward, what's going to change to make that better?
I can start with that. Well, so that's a great question, Steve, and I'm very familiar with the Valley of Death, having tried to get through it several times in the past unsuccessfully. The big change really is the new program, right? The Space Technology Program in particular is set up to get through that valley and to deliver technologies and capabilities beyond TRL of 6, so beyond testing in a relevant environment. In addition, that cross-cutting capability demonstration program that I mentioned quickly will only sponsor technologies in which a customer has already been identified and in which that customer is actually providing a portion of the funding for that demonstration to prove their interest in flying that technology in the future. So we'll have a handshake deal up front, along with some cash, actually, from that customer to fly that technology on some future mission. And then through this new program, which I need to tell you didn't exist previously, we'll have the capability to take these technologies from concept all the way to flight.
The tough part, of course, is always protecting technology funds when money
Absolutely.
gets tight, and I wish you the best of luck with that.
Thank you.
Thank you.
Hi, my name is Jim Fenton. I'm at the Florida Solar Energy Center, just 15 minutes away. I agree. This is about technology. I've heard innovation. I've heard agile. I did not hear inspiration. I heard motivation. Motivation is to push people to do things they don't want to do. NASA famously inspired a generation of future scientists and engineers. I want NASA to do that again. I want inspiration up there with the words innovation and technology. Thank you.
Thank you. And our guest of honor, we will make an exception, please. I'll never hear the end of it if this session overruns, so.
Norm, thank you, and
Sure.
thank all the panelists. I tried to be in a number of the sessions. My name is Sheila Jackson Lee, and I come from Houston, near the Johnson Space Center. First of all, I think we did have some inspiration today, and I think that's an important point. I keep trying to grow physicists and the number of body politic for science in America, so this is an important element. I also think Ed's point about the Soyuz was an interesting point. The President's points about Orion is another interesting point. My question is that we have interrelatedness between the centers. I'm obviously hearing from constituents all the time about jobs, the economy aspect of it, but preserving the science, the intelligence of it, if you will, the knowledge. My question is, in this period of time when people were geared toward one program, and I thank the President for his message and his inspiration, what are we doing with that body of human resource right now? You're talking about new technology. Ed, do we go to, if we just put the President's speech here and just say, let's go do and build a Soyuz, what do we do right now? That's the fear. That's the apprehension for individuals who are right in the midst of these centers right now, in particular where I am right now, Kennedy, and then Johnson in particular.
That's a great question to close on, and Doug, I think we'll let you take that one on.
Right. Certainly that is an area that we are working very hard on. When the budget request came out, we put together teams to go look at these, not only these new programs that we've been assigned, but also we put together a transition team to go look at the very thing that you're talking about. How do we? It is a shift. It is a shift in priorities and policy in terms of how we go about exploration. And so it is important that we work through that carefully, because these are our people too, and people that we've worked with for many years. And me personally, I spent 32 years at Johnson Space Center before coming to D.C. So it is definitely something that we take very seriously and are working on.
I think, Yolette, a lot of us will need to work with you.
Yes.
What I gleaned today is that you have put forward, somebody's heard me say this many, many times today, an onion, and we need to peel the layers and find out where we fit. Onions sometimes sting, but they are pretty tasty. But I think it's important that we've got to calm people and use the genius that we have in all of these centers and produce something for America. That's what I think is enormously important. And I hope we can be around the table really with our sleeves rolled up, really helping to produce it, and it's not done, as I know that you're not doing it, but not done in isolation. There are so many moving parts to this.
That's a perfect wrap-up for us. Thank you for doing that. Let me special thanks to Doug and Bobby and Ed for their remarks, and they've got a big challenge ahead, particularly our NASA folks here, current NASA folks. And thanks to each of you in the audience for your questions, and to those who are out in cyberspace, we appreciate your interest. I believe we're supposed to go back to a broader session now, and somebody will guide you if you go out this door right here. Thank you all very much.